Well, welcome, and would like to talk a little bit about modeling substances in your engineering and thermodynamics classes. I got a couple of show and tells to show you. So what do you figure? What do you figure is contained inside this tank? Okay. Well, if you saw that, well, gosh, looks like the label was a giveaway. Let me move the it's compressed air. It's compressed air at about 90 psi gauge. So if you had some type of engineering or homework problem associated with, if you knew the pressure, the volume, and the temperature in this tank, now you can see that I'm holding it. So the contents of the tank are about at room temperature. How would you model what's inside this tank, compressed air? How would you model that compressed air? All right, another show and tell. What do you figure is contained inside this glass tubing that's arranged in this interesting shape? So your common sense tells you that what's inside this would be neon, the gas neon. And if you knew the volume, you knew that you could calculate the volume inside this bent tube, and let's see the pressure. Well, we don't know the pressure, but you might be able to look up neon signs in Wikipedia, and I'm confident they would tell you about what the pressure is inside this. And look, I can touch, this is room temperature to the touch, so I can touch it. So the contents of this, the neon in here would be about room temperature. How would you model that? Well, that's what this module is all about. So let's get started. So this module has to do with the compressibility factor Z that you're going to find in chapter 3 of your textbook that talks about properties. And so here's a objective of what I'd like to cover here in this video. First is let's review your knowledge of an equation of state. What's an equation of state? Let's review your knowledge that you've learned already. What are the properties at the critical point of a substance? What do you know about an ideal gas so far? Now, sort of in engineering and decision making, when is a gas not like an ideal gas? When can we model our gas as an ideal gas, and when can we not? And that's going to bring up the topic of what Z is. And so we're going to talk a little bit about why is there a variable called Z in the first place in chapter 3. And then, of course, numerically, how do I determine a value for Z? And then last, want to show you some examples of how to apply Common Sense 101 to the modeling of ideal gases or non-ideal gases. So here we go. Review. What's an equation of state? So this should sound familiar to you. I hope. Let's review just for completeness. An equation of state is a mathematical expression, an equation, okay? And it relates the pressure, the specific volume, and the temperature of some substance, okay? And so here I've written out a general sort of mathematical expression. P, the pressure, is some function of V, little v, and T, specific volume and temperature. Or an equation of state could be V equals some function of pressure and temperature. Or temperature equals some function of pressure and specific volume. I think you get the idea that equation of state, you can think of it as a formula. And so to put it all together, it says the state of any substance is defined by any two of these three properties, any two independent properties. You got to be sure that the two properties that you select numerically are independent of one another. Okay, I think you have a pretty good idea for what is an equation of state. Now, equations of state, here's a little sampler, examples of equations of state. Now, there are lots and lots of equations of states for gases based on years and years of scientists, research, observation. And so let's review just three of these. First is the Beatty-Bridgman equation. And so, of course, we're not going to go into the details, but do you see visually that here's the equation of state, pressure equals some formula, but do you see that the formula is a function of temperature, specific volume, and some other constants, capital A and capital B, that are further defined? All right, that's an equation of state. Messy, but an equation of state. The van der Waals model equation of state, van der Waals, okay? Let's see what the form of that is. It says RT equals some function of pressure and, well, this turns out to be specific volume. Vm is going to be specific volume. But do you see that the form of this equation of state is temperature equals some function of pressure and volume? And it says in Wikipedia, they rearranged the equation to solve for P. And so here you've got P as a function of temperature and specific volume. The third example is the one that you're praying for in your class, isn't it? Right? You want to keep things as simple as possible, and practicing engineers want to keep things as simple as possible to get to make some decisions in their design, in their analysis. And so the ideal gas model, P times little v is equal to RT. Another way to say it is P times capital V equals MRT, or rho equals P over RT. All those three are identical. So those are three examples of equations of state. Okay, now, as we continue our crash course, refresh your memory on where's the critical point on a pressure volume diagram. So remember the phases. You remember the phases of substances? Underneath the dome, the phase would be a saturated mixture. On the left side of the dome, it would be a saturated liquid. On the right side of the dome, that would be a saturated vapor. Things to the right of the dome would be considered superheated vapors, and at times ideal gases. And then to the left of the dome is compressed liquid, like tap water. Okay. The critical point has got three properties associated with it, depending on the substance. The critical pressure, I'll call it P crit. The critical temperature. Here's a line of constant temperature that passes through the critical point. So we label that isotherm, T equals T crit. And then finally, the specific volume at the critical point, V crit. Okay, I think you got a good handle on that. So be aware that these critical point properties, T critical, P critical, and it turns out you can calculate V critical using this, okay? A little more later on that. But the critical point properties, temperature, pressure, specific volume, fully depend on the substance of interest. So notice these different substances. Here's air, here's ammonia, here's argon, et cetera, et cetera. All of their critical point properties are different and unique because they're different substances. Okay. Now, what's an ideal gas? So now we're into chapter 3. Your professor, your instructor has revealed the ideal gas equation of state. You say, man, this is really pretty easy. This is what I'm hoping for. Just some reminders. It is my hope that you've got this top equation of state in your head. So I've drawn your head and a double arrow. So your head and this equation of state should be 1. All right, PV equals MRT. You should be able to quickly derive these next 3 identical mathematical statements. P times little v equals RT. Remember, that's V over M. Little v is V over M, okay? Then solve this. V, solve for V. V is RT over P. Little v is RT over P. Remember that the density, rho, that's not P, that's Greek letter rho, is the reciprocal of specific volume. So rho is P over RT. You should have this top one in your mind, and you should be able to quickly jot down with pencil and paper these next 3 immediately. Now, what's R? So we go back to PV equals MRT. What was R? Well, R is called the ideal gas constant. and it's defined, R, the gas constant for each substance, is defined as R bar over the molecular weight. And R bar is a universal gas constant. And here it is. You better be able to find this one page of constants and conversion factors and print it out on paper. So that's how, and you should commit R bar to memory, both in SI and English units that I've circled. You should have that committed to memory. But then at a minimum, you've got to get that on a formula sheet if you're allowed to have a formula sheet. Okay. Molecular weight units, molecular weight are in kilograms per kilomole from freshman chemistry, or pounds mass per pound mole. You should know the molecular weight of hydrogen, H2. It's 2. You should know the molecular weight of nitrogen, N2. That would be 28. And since you're an engineer, you're getting ready to be a practicing engineer, you should also know that the molecular weight of atmospheric air is 28.97. You should commit all that to memory. Okay. So once you've got these molecular weights in your head and you've got R bar in your head, you should be able to quickly identify R, or determine R. So recognize the units of R are kilojoules per kilogram degree K, or in English, foot-pounds force per pound mass degree R. So I declare you an expert in R, determining R, the ideal gas constant for any substance. What are some commonly observed ideal gases? Quick list. You can think of more than this, but here's just what came to my mind when I was preparing. Atmospheric air, air contained in your living room, the air throughout the earth, on top of the earth. Okay. Compressed air, the air inside this tank at a higher pressure. Okay. Here's a tank full of argon used in the welding industry. Okay. Here's the neon contained in neon signs you commonly see. And here is helium contained in helium balloons for parties. Okay. Those are commonly observed ideal gases. Let's look at some examples of things that are not ideal gases. Well, here's a chef pouring a large, he's got a large cask full of liquid nitrogen. So it is N2, but you can see with your eyes that this is not a gas. He's pouring liquid nitrogen out of his cask into this bowl, and in the bowl you can see with your eyes, you can see a liquid level there, and you can see condensing nitrogen vapor that's kind of pouring up out of the bowl. Okay, so you can see with your eyes, this is a saturated mixture of N2, not an ideal gas. Now, a little more, let's be a little more generic in terms of helping you with your problem solving. Pressure volume diagram with a vapor dome. Any dot that you see, any state, each one of these dots is a state. Any state that you see that's under or on the dome must not be modeled as an ideal gas. Not ideal gas. You got to commit that to memory. Under the dome, on the dome, not ideal gas. Okay. Another example of not an ideal gas is the steam, the superheated vapor steam that's going into a steam turbine. This is a cutaway view of a real steam turbine. This is the steam going in. It's admitted to the inlet stage of this rotating disc with these blades on it. So the steam rushes past those blades, and that's what enables those blades to turn the shaft at a certain torque and speed to produce power. The steam going into the steam turbine is not modeled as an ideal gas, and here's why. Because typically, if we were to plot, if we knew the pressure and temperature of this superheated vapor, you would find that this state is somewhere in the general neighborhood of the critical point. It'll be below the critical point pressure, okay, but it'll be just in the general neighborhood. So we can't model this steam as an ideal gas. Cannot model H2O as an ideal gas in this situation. Too close to the critical point. And so similarly, now let's generalize to all substances. So I've drawn a bunch of dots that are in the neighborhood of the critical point on the vapor dome. And so the point there is I've turned my box yellow. Not going to be good to model any of these states as an ideal gas. So here's what we do. What we do is we use the compressibility factor capital Z. It's a dimensionless number. And we use that to describe an actionable equation of state for what we might call a real gas. Okay, a real gas. And it's the equation of state is PV equals ZRT, where Z is a dimensionless number. Okay, so now it remains to, in chapter 3 and in engineering practice, it remains to figure out what is the numerical value of Z. So some of your homework problems are going to involve what's the numerical value of Z. I'm going to try to help you with this. Okay, so what is Z? I want to chase you back to your book to do your reading. Sections 311.2 and 311.3 fully cover the compressibility factor Z. I want to suggest you read your textbook in addition to looking at this video. Let's compare this non-ideal gas equation of state to the ideal gas equation of state. So let's look at it with our eyes. Left-hand side, identical, PV equals. Right-hand side, ZRT for non-ideal gas, RT for ideal gas. Let's see. Is it pretty obvious? When could you model, if you determined a value for Z, when could you say, look, I think I've got an ideal gas. I'm going to model my engineering problem as an ideal gas. That substance will be an ideal gas. It's when Z is 1.000, okay, or damn close to 1. Okay, so that's your powerful and practical conclusion of working with Z. If Z is close to 1, you as an engineer are entitled to model your substance as an ideal gas. Recognize that Z is dimensionless. You got it? Okay, here is a roadmap for how to determine Z. I'm going to go step by step by step and then try to give you an example here shortly. First, step 1, determine R for your gas. R is R bar for the molecular weight. Next, you're going to go to a table in the back of your book and you're going to write down P critical and T critical, the critical point pressure and temperature. You will need to know the pressure and temperature of your substance, and you'll calculate what's called the reduced properties. The reduced properties, and they're called P sub R and T sub R. These are, do you see how these are dimensionless? So be sure that your temperatures are in absolute temperatures, absolute either degrees K or degrees R, okay? Pressure units must be identical for both P, your pressure, and the critical pressure, okay? Determine those two reduced properties, dimensionless. You're going to go to the back of your book and go to either figure A1 or A2, some more details later, to pinpoint your lines of PR and TR. It's that easy, okay? You're going to find the intersection point of those two lines. They're going to intersect, and then you're going to read horizontally to the y-axis to determine the value of Z. And that's simple. Okay, so let's see. How are you going to get R? You're going to go to table A1. You've got your substance. You'll write down, if you cannot remember the molecular weight, a few things you should know by heart. But if you don't, if it's if it's refrigerant R134A, you will not have memorized that the molecular weight is 102. So so you'll write down the molecular weight of 102. That's the way you get R. Also, while you're there, you'll write down T critical and P critical, the critical temperature and the critical pressure. You write those down. Then, on your paper, determine P sub R and T sub R. P over P critical, T over T critical. Next step, let's see if you're on figure A1. Okay, there may be situations where you're off the chart. That's when you're going to go to figure A2. But let's look at figure A1 first. Notice here, the x-axis first. The x-axis is P sub r, reduced pressure. It ranges from 0 to 1. Realize there can be pressures that are reduced pressures that are higher than 1.0. It can be 10. You have to go to a different table figure. Okay. Notice how all these parameter lines are expressed in terms of T sub r. Starts out at 5 and decreases and decreases and decreases until TR is 1.0. Okay. So recognize here. So do you see how you've got your PR, you've got your TR. So you seek the intersection line. Where do your two lines intersect? Read off horizontally and read the resulting Z. It's as simple as that. Now, let's say you didn't fall. Let's say your pair of PR and TR did not land on figure A2. Let's say your reduced pressure was a large number or a tiny number. Okay. Let's look at figure A2. So figure A2, also on the x-axis, your reduced pressure, PR, ranges from 0 all the way up to 10. Okay. Your reduced temperatures, let's see where they are. They range from 1.0 down low, increasing, up here to 3.5 for this part of the chart. But now we've got another part of the chart that's way up here. It's two charts rolled into one. Interesting thing here is we've got T sub r values of 5, 7, 10, and 15. And imagine if your TR was 30. If your TR was 30, where do you, it's not shown, but doesn't common sense say that if TR was 30, it would be a little bit below that straight line. And what practical conclusions can we make from here? Look, here's Z of 1.0. Here's Z of 1.0. But up here in this upper graph, Z of 1.0, do you see that if your reduced pressure, P sub r, is less than about 1, then you're an ideal gas. So for low reduced pressures, you're an ideal gas. Also, if your T sub r is big, let's say 10, okay, you see that certainly you're going to be down near 1.0. So ideal gas, when TR is greater than 5 and PR is less than 1, it's a no-brainer. You are entitled to model your substance as an ideal gas because you're seeing that Z is 1. That's the big practical conclusion for all of this. Now, on the other hand, if you find that Z is 0.7, all bets are off. Somehow, if you find that your Z is 0.7, you are not entitled to model your substance as an ideal gas, and you got to do some head scratching and do some other tricks. So, but you still got an equation of state. If all you have to worry about is calculating changes of specific volume from state 1 to state 2, you still have an equation of state, PV equals ZRT. P1V1 equals Z1 R T1. So it's at least you've got something to work with in the real gas department. Okay, you think you got it? Now let's apply some common sense. I want to give you some examples of applying common sense 101 to the engineering task of modeling substances and praying that you got an ideal gas. So here's a little decision tree for you. Is my substance commonly recognized as a gas? You ought to be able to answer that yes or no. As a young engineer, is it commonly recognized as a gas or not? If not, so for example, if you've got H2O in this class, it's not commonly recognized as a gas. If you have refrigerant, not commonly recognized as a gas. Propane, clearly not commonly recognized as a gas because we engineers are working usually with those substances as in different phases. Okay, in that case, you're going to use property tables for pressure, specific volume, temperature, internal energy, and enthalpy relationships. You're going to use tables. All right. Let's say you do have a commonly recognized gas. Let's say nitrogen, oxygen, hydrogen, helium, the things that we recognize as ideal gases. You'll need to check Z. Now, does a quick check of Z reveal that Z is 1.0? Wow. If it does, as an engineer, you say, I've got an ideal gas. I'm going to model my substance as an ideal gas because I checked Z. It was 1.0. Got it. Okay. If Z was not 1.0, then at least you have the equation of state PV equals P times little v equals ZRT, or V is equal to ZRT over P. Okay, so that's where you would end your problem-solving capability at for this class for non-ideal gases, or what we would call real gases. Now, there are plenty of commonly observed gases that we are fully entitled to model as an ideal gas, and it's real. The air around us is real. It's not a figment of our imagination. And we model the air around us as an ideal gas. So let's do an example problem. Let's verify that the room in our living room can definitely be modeled as an ideal gas. What will we do? All right. Table A1, we'll go and look for equivalent air. Air is that mixture of mostly nitrogen, some oxygen, and some other constituents. The molecular weight of our air is 28.97. The critical temperature, the critical point temperature, 133 K. The critical pressure, 37.7 bars. So let's work in English units. Okay, the critical pressure is 30.7 MPa. I transformed that to 5,468 pounds per square inch absolute. The critical temperature, it's cold. 133 K is minus 220 degrees F, or 220 degrees R. That's cold. Okay. Our room pressure, the pressure, absolute pressure in the room, about 14.7 psia. That's 1 atmosphere. Room temperature, let's say about 70 degrees F, give or take a few degrees. That's 530 R. So I will calculate P sub R. 14.7 over 5468 is 0.0027. T sub R, 530 divided by 240. Okay, have I got that? Yes, there's 530 room temperature, 240 T critical. Yep, 2. TR is 2.2, or about 2. Let's go to our chart to find Z. Okay, so let's see. X-axis, reduced pressure. We're just about here at 0.0027. So I cheated and drew my arrow further to the right than it really should be. Okay, let's find our reduced temperature value of 2.0. Here it is. I've circled. It's incredibly hard to see on the screen, but we'll find the intersection point, and there it is. And so do you see, this is a no-brainer. We've got Z as 1.0. As engineers, we're going to model the air around us as an ideal gas. Powerful, powerful verification. So in other words, we don't have to be told. We don't have to be told by a professor or told by a senior engineer to treat the air around us an ideal gas. We can prove this. We can prove it with facts and fundamentals. Okay, so where does our living room air fit on the PV diagram? Here was the critical point we looked up. And here we are, sort of, we're not really to scale, but recognize that we're at a much lower pressure than the critical point pressure, and we're at a higher temperature than the critical point temperature. So we're way out here on the vapor dome. Okay. We're perfectly valid to model room air as an ideal gas. Okay. You can go through the same drill with the compressed air in the tank. You get about the same results. Here's some real, honest to goodness, real world compressors. Okay. Centrifugal air compressor. This is a positive displacement piston and cylinder air compressor. Now you say, okay, here's one example of gases but it's a cryogenic process. So keyword cryogenic, low temperature. So Linde is a very well-known manufacturer of bottled or put gases that are placed into tanks and sold to consumers. Linde, very well-known manufacturer. And as part of their process that I've shown here, the part of the process involves cooling atmospheric air to very low temperatures near the critical point, and then stripping out the various constituents from atmospheric air and selling those gases to consumers. So when you see the word cryogenic or extremely low temperatures, not ideal gases. So let's look at our PV diagram again. And you say, whoa, I've got red and I got green and I got yellow. I've tried to color code for you examples of when you can pinpoint your state. How would I model my substance? Well, turn anything under the dome is red. Phase change substance, definitely not ideal gas. When you're close to the dome, when you're perilously close to this dome, you must check Z. Numerically check Z. Okay. When are you in the green? Well, you're in the green when, and I've made a little note, when T sub R is greater than 5 and P sub R is less than 1, you're very well able to model that state as an ideal gas. Okay. It's my hope that your instructor will give you some additional practical guidance. And then when there's a question on a, let's say a high pressure time, like taking a test where time is limited, it's my hope that your instructor will guide you and say, treat air as an ideal gas. And that's fine. That's fine, because we don't want you to have to go and check Z in a high stress situation for air every single time. So that's definitely fair game, or that your instructor would give you that guidance when you have the word air, some guidance on, yeah, just treat it as an ideal gas. So a little reminder, engineers make these decisions all the time using a combination of two things. One is knowledge of the fundamentals. That's why you're taking this class, getting knowledge and problem-solving capability for the fundamentals of thermodynamics, coupled with working experience. And so when I'm working with students, a lot of times, when they'll say air, I say, oh, that's an ideal gas. And they kind of look at me and ask questions. And I say that my jumping to saying air is an ideal gas comes from working experience. Okay. And you're getting that right now through your problem solving, through co-oping, through internships, and then ultimately you're starting work as a practicing engineer. And so I'm not a fan of the word assumptions. Assume that, because really it's up to the engineer to model the substance, not just assume it's an ideal gas. Okay, so do you get the idea that you could be given a steam turbine problem and write down, assume it's an ideal gas? Well, you'd be way off. That is not a good engineering model for steam vapor under any conditions. Under most conditions. So anyway, the idea of assumptions, I'm not a big fan of that word assumptions. Big fan of you getting the fundamentals and then gaining experience to make these modeling decisions. So let's recap what we covered here. It's important to understand what equation of state means. And boy, particularly, you should know by heart the ideal gas equation of state. P times little v equals RT. Understand the purpose of what Z is all about. Okay. Understand how to determine a numerical value for Z. If Z is 1, then you got an ideal gas. Okay. And understand how to determine and work with Z is PV over RT. And then finally, with all of that coupled with some work experience, understand how to model any substance so you can get those thermodynamic properties. Okay, I hope that has helped you get a better working understanding of what Z is all about. So again, remember, so Remember, what's in here is this glass tube has not warmed up a bit since I started. It's just as much room temperature as it's always been. So go Hokies, and look forward to seeing you next time.